In this video, I'm going to prove that the limit of f of x, if it exists, is unique. And this is a great time to do a proof by contradiction. That is, suppose that it's not unique. Suppose there's two limits. Suppose that the limit as x goes to a of f of x equals L and the limit as x goes to a of f of x equal m, where L and m are not the same. So somehow we need to get a contradiction. And what are we going to contradict? Exactly what we're supposing, that L and m are different. I could say that the limit of this equals L and the limit of that equals m, and it can be true if L equals m, but if L is different from n, it is not true. Okay, so let's write down what these two statements here mean in blue. The limit as x goes to a of f of x equal a implies or is the same as, given any epsilon greater than 0, there exists a delta, call it delta 1, greater than 0, such that, I'll save this, such that whenever 0 is less than x minus a is less than delta 1, then f of x minus L is less than epsilon. I'm going to do the same thing for the limit equaling m. The limit as x goes to 0 of f of x equal m is the same as, given any epsilon greater than 0, there exists a delta 2 greater than 0, such that whenever 0 is less than the absolute value of x minus a, which is less than delta 2, then the distance between f of x and L is less than epsilon. Now, just to get everything in the same language, we are going to choose delta to be the minimum of the two deltas, delta 1 and delta 2. So this tells me that given any epsilon greater than 0, there exists a delta greater than 0 such that two statements are true. Whenever 0 is less than x minus a, which is less than delta, we have two things. We have that f of x minus L is less than epsilon, and f of x minus m is less than epsilon. Well, if you think about it, if L and m are different numbers, if this is L and this is m, well then I can get f of x so close to L depending if I pick the right epsilon, that it's not including m. But this says that f of x minus m, or f of x is within epsilon of m. But that's not true. Up here would be L plus epsilon, and down here will be L minus epsilon. So let's see, so we're doing the limit at A. So here we have A plus delta, and here we have A minus delta, and it turns out that whatever the function is, f of A minus delta maybe is L minus epsilon, and f of A plus delta is L plus epsilon. Maybe the curve goes like that. So every time I pick a neighborhood around a delta neighborhood around A, the image f of all of these numbers end up between L minus epsilon and L plus epsilon. But wait a minute, they're supposed to be getting closer to M, and they aren't. If I make a smaller epsilon, I'll only be within that range of L. So it can both happen at the same time. Now, I'm saying that for any epsilon, there exists this delta. But this actually isn't true. If we look at, and it better not be true, if we just look at this, L minus M, L minus M. Now, this is the same as L minus f of x, plus, let's put that in another color, L minus f of x plus f of x. So basically, what's in blue is 0 minus m. Well, that's certainly true. And whenever you have the absolute value of one thing plus another, there's their plus sign, you can use the triangle inequality and write it down like this. Now, in absolute value, you can switch the distance. That is, the distance from L to f of x is the same as the distance between f of x and L. Don't have to do anything there. Now, what I'm going to do is, let me put it over here. Choose epsilon to be L minus m over 2. Okay, so this here, what I'm about to write is strict, so I should have equal here. This is less than, well, this is less than epsilon, which is L minus m over 2, plus this is less than epsilon, which is L minus m in absolute value over 2. Ooh, look at this. This is L minus m. Now look at what we have. Here's our contradiction. We have the absolute value of L minus m is less than the absolute value of L minus n. That is, we showed that something is strictly less than itself. That can't be. That's the contradiction. So L equals m. That is, limits are unique. Limits are, in fact, unique. And that proves this theorem. Please leave a comment letting me know how much you disliked it or how much you like it. If you know a better proof of it, anything you like to leave in the comment related to the video. Another thing is, if there's any theorems you like for me to prove, put in the comment section. I'll give it a try. Okay, thank you, and most of all, watch and learn.